Oke, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome back again to Process Synthesis and Simulation class with me, Hani Prastiawan. And today we are going to discuss one of the another equipment existed in the Aspen Plus, which is reactor. This equipment is the main equipment in chemical engineering processes, which is well, there are two main processes. There is a reaction, which is a reaction, and also separation. The reaction is using a reactor, while the separation is using separator. What that which already discussed in the previous meeting. So in the aspect class, there are two types of reactor that can be simulated which are non-kinetic reactor and also the kinetic reactor. You can see that in this picture there are 7 types of reactor. There are R-stoic, R-yield, R-equal, R-gibbs, R-CSTR, R-plug, R-batch. So the non-kinetic reactor, you can simulate it using R-yield, R-stoic, R-equal, and R-gibbs. The equation used in here you can see one by one in the Aspen Plus. In a yield and R-stoic, you can directly stated how much of the conversion that you wanted and how much is the yield of the product that you wanted. While in equilibrium reaction, of course, in here, in this type of reactor, you can find the equilibrium conversion by using uh, thermodynamic model, which use a Gibbs free energy. And the last one, the kinetic reactor. There are 3 types of reactor you can be used in the Aspen Plus. There are R-plug, RCSTR, and R-batch. R-plug is a reactor which where the conversion is a function of the length of the reactor, while the CSTR stands for the continuous stir tank reactor. The conversion of the reactor is based on the volume of the reactor, while the batch reactor, the conversion is dependent on the reaction time or uh, the time dependent variable conversion. So this is the basic explanation on the each reactor, and in this simulation we are going to divide it into 2 simulation. We will start with the non-kinetic one, and then we continue for the kinetic reactor. There, this one is the example. I have an ammonia reactor in here. This one is the reaction when the nitrogen is reacted with the 1 mole of nitrogen reacted with 3 mole of hydrogen. It will form 2 mole of ammonia, and the reaction is uh, forward and backward. So it must have an equilibrium conversion. It has a forward reaction to form ammonia and also a backward reaction that can separate the ammonia into nitrogen and hydrogen. The reaction occur at the 550 degrees Celsius and isothermal. The pressure itself is 175 kilogram per centimeter square, and the property method used in here is an RTL, and the feed contains air 5,000 kilogram per hour and also the hydrogen 5,000 kilogram per hour. You have to pay attention on this information. The air is 5,000 kilogram per hour, so you have to specify your air into oxygen and also the nitrogen. So the nitrogen will get we can get the nitrogen from the air. Each feed condition is at the room temperature 30 degrees C and also 1 atm. So you have to calculate, you have to find out the gas outlet composition of the reactor if the nitrogen conversion is 0.8 of the equilibrium conversion. So there are two conversions shown in here. First one, you have to calculate the equilibrium conversion. You have to calculate the equilibrium conversion. You can use either by using R equal in here, yeah. You can use R equal or R Gibbs. And after that, once you can calculate the equilibrium conversion, then you just continue to, to use another reactor in the Aspenpal, which is you can use either using R stoic or R yield. And then you can specify the nitrogen conversion is 0.8. And after that, you can get the gas outlet composition. So this one is the simulation step. You have to finish the reaction in the reactor equil, and then you calculate the equilibrium conversion, and then you can after that you calculate the conversion of the nitrogen in the RS stoic, and then you simulate the ammonia production from nitrogen and hydrogen in the RS stoic. So actually in here I have a question, but since this is an offline video, then you can just follow the step by step. Actually there are two you can see that the inlet feed is at 30 degrees C and 1 atm. However, the reaction occurs at 550 degrees C with the pressure of 175 kilogram per centimeter square. What are you going to do first? Are you going to increase the temperature first? After that, you increase the pressure, or you increase the pressure first? After that, you increase the the temperature. Actually, there's a question. Why? Why? Which one are you going to choose? You, you first increase the pressure, and after that increase the temperature, or you are going to uh, increase the temperature first, after and followed by the increasing the pressure. Actually, how to answer this question? You have to you can manually calculate the by assuming a case ideal calculation, which one is more effective. And actually in this simulation I already shown you that the most effective one is increasing the pressure first, and after that you can follow by increasing the temperature. So this one is more effective compared to while increasing the temperature first and followed by increasing the pressure. In terms of the energy and also in terms of the economy, it is more effective. And the answer is you can try to do it by yourself and compare the result. How much energy is used while when you are using this arrangement, or compared to the heating and also increasing the pressure arrangement. You can compare how much is energy used, or how effective is the arrangement can be made for this process. So we are going to go to the component. I will do like this. So we are going to enter the nitrogen, oxygen, hydrogen, and ammonia. Okay, hydrogen, nitrogen, oxygen, and ammonia. And for the thermodynamic model, you can choose an RTL. Just click next, and then in the best method you can find an RTL in here, and click next again, and go to the simulation environment. Okay, for the arrangement, in the main flow sheet, you can put two compressor in here, and then two heat exchanger, one mixer, and also one reactor equilibrium. Yeah, two compressor, two heat exchanger, one mixer, and also one reactor. C101, C102, E101, E102, mix 1, and R101. So you can find the compressor in here, the pressure changer. This one is C101, and then another compressor for one C102, and then you can place an exchanger in here, E101 and E102, and then you mix these stream. You can go to mixer and or splitter in here. I give a name of M101, and also the reactor we are going to use first is reactor equilibrium, R equal R101. And then for the stream name, udara means air, yeah? Air. This one is the hydrogen, and the outlet is like this. Okay, I'm going to use this one, air, and then this one is for the flow of the hydrogen, and then connect the outlet of compressor to the exchanger. This one is stream O2, this one is stream O1, this one is stream 03, and from the exchanger 102 stream 04, this one, oh sorry, that one is the basic mistake. When you are doing something like this, then you will find one white arrow near the main equipment, so you have to cancel it, and then you put it correctly on the red arrow, and it will turn into a black arrow like this, and you can name it into R1 in. This one is R1 out 1, if I'm not mistaken, if I name it before, R out 1. It's okay. R2, R1 out 2. Okay, so make sure on the red arrow is already changed into a blue arrow. It means that your stream is perfectly connected to each other's equipment. And after that, what are we going to do? Let me see. You have to input the specification for the air. So you can go to the stream and then go to the FR, and you put the information in here. The temperature is 30 degrees C. The pressure is 1 atm. 1 atm. And also the flow rate is 5,000 kilogram per hour. While the composition, you can change this one into a mole fraction. The mole fraction is 0.79 of nitrogen and 0.21 of nitrogen. While for the hydrogen flow rate, the temperature and pressure is the same, which is 30 and also 1 atm. The mass flow rate is also 5,000 kilogram per hour, while the mass flow you can put in here like this. You can see the difference in here. The total basis is keep empty, and the information is written in the composition. You can do something like this, or you can also do something like this. You put the total mass in here, and you put mole fraction in here, and the hydrogen is 1. It is the same. And then we go to the compressor. We put information for the compressor. In here, the compressor is an isentropic and with the discharge pressure of 175 kilogram per square centimeter. We just put in here the isentropic. Actually, there are different calculation. Actually, you can just by clicking this question mark, you have to be taken into a specific information about the compressor. See in here the compressor efficiency, and then there should be an explanation with the compressor type, specifying compressor. See in here if you click the question mark in pages where you are stuck, then Aspen will tell you what you have to know about the equipment, or what you need to know for each variable in here. So you can choose the discharge pressure in here and you type 175 kilogram per centimeter square. Compressor 2 also have the same specification, isentropic and 175 kilogram per square centimeter, while the heat exchanger we can just specify the temperature into 550. Pressure keeps maintained at the 175 kilogram per square centimeter. Heat exchanger 2 also the same, 550 with the pressure of 175 kilogram per centimeter square. Done. Oh, we forgot to enter the information for the reactor. For the reactor, you can put the information of the temperature in here, and the pressure is 175. You have to make sure that the unit is the same with the uh, question. Yeah? And then for the reaction, in here you can put the reaction that can be occur in the reactor. Since we have only one set of the reaction, which is production of only ammonia from the hydrogen and also the nitrogen, and this one is the ammonia. You just have to write the coefficient based on this. How many moles of nitrogen, how many moles of hydrogen, and how many moles of the ammonia in here. 1 mole of nitrogen for in the stoichiometric one, from the stoichiometric chemical reaction. 1 mole of nitrogen, 3 mole of hydrogen. So you can type in here 1, 3, and 2 for the ammonia. And then after that, you just keep it empty, so we can get the equilibrium conversion for this reaction without specifying anything. Yeah, without specifying anything in here, you let Aspen find out or calculate how much is the equilibrium conversion of the reactor. However, you cannot calculate it. You won't get it directly, the conversion, but you have to calculate it manually from the simulation result. So all information have been added like this one. You can, if you make a mistake or there is an error at the end, you can check your reaction by clicking this reaction and edit. You can see that in here If you want to add another reaction, let's say in the reactor you have 6 or 7 reactions, then you can add new reaction in here. But in here, in this case, we only have one reaction, which is hydrogen, 1 nitrogen of hydrogen, 3 mole of nitrogen, and 2 mole of ammonia. Okay. Next, we can calculate the reactor. I make a mistake. Sorry. It is correct. Which one is not correct? Oh, sorry. I make a mistake. Sorry, this one is the 3. And this one is 1. 3 hydrogen, 1 nitrogen. Sorry. Close. Uh, After you make a simulation, please don't forget to reset. You can reset the simulation so that if there is an error, and the Aspen Plus will wipe the memory and then start new simulation. Okay, results available. You can check the result in the result summary, and then from the stream in here, actually you can copy the information to Excel like this by clicking this one in the corner left and copy all, and then you can open Excel and paste on the stream is shown in this Excel. So how to calculate the reactor equilibrium? You can just go to the reactor detail. In here, uh, the reactor outlet, there are two reactor outlet 1 and also reactor outlet 2. It indicates that the phase can be separated into vapor and also liquid. However, in this simulation, you can only found one phase, which is gas, which is gas. So for the calculation, then I will select this. I will freeze the header. Review, which one? Freeze. Okay. Freeze, and then you go to the mole fraction, mole flow. Yeah, mole flow. Sorry. You can go to the mole flow, and then you choose this one, nitrogen. The nitrogen information. This one, you can calculate the equilibrium conversion by using nitrogen inlet and nitrogen outlet. So the X equilibrium equals to uh, nitrogen in minus nitrogen out divided by nitrogen in times 100%. I think I don't have to explain it again. You must have already know on how to calculate this one. In this one I can also freeze. Okay, no, it's okay. This one, so the nitrogen inlet is this one, and then the nitrogen outlet is this one, divided by the nitrogen inlet and times 100. This one is the equilibrium conversion of ammonia production from from nitrogen and hydrogen. So the equilibrium conversion is 52.07331. And the next question is, what if I want to simulate with the nitrogen conversion of 0.8 times the equilibrium conversion? Means that the conversion of nitrogen will be 0.8 times uh, equilibrium conversion. So you can just multiply this value into 0.8. You will get 41. You can copy and paste the value in here. So I can copy this one, and we go back to the PowerPoint. See, this one, actually I don't have to calculate the conversion. In the class, I usually ask the student to calculate the conversion, but I already show you on how to calculate it. So the stoichiometric the equilibrium conversion is 52.07, and then for the conversion of the stoichiometric, you multiply this value with the 0.8, just like in the question in here. The nitrogen conversion is 0.8 of the equilibrium conversion. So after that, you can use another reactor in here, which is a stoichiometric reactor. So in the Aspen Plus, you have to add another reactor, which is stoichiometric. I put it in this one, R102. Oh, wow, it is quite heavy. And then, since we are going to use the same inlet, I think you still remember the equipment that can be used, which is a duplicator in here. Duplicator 110. Okay. I just learned that my Aspen is very heavy. Once I open Excel, Microsoft Excel together with this Aspen, if I close it, then the Aspen will run smoothly. So I already have a duplicator in here, and then I have to reconnect the source. See, the source currently the source is connected to M101, but I want to move it into a duplicator. So I just want to reconnect the source into a duplicator, and I connect the M101 into a duplicator in here. This one is stream 05. This one also R2 in. Yeah, R2 in. And then this one is the R2 out. Okay, finish. Last one, you just have to enter the information for reactor 2. The temperature is 50 degrees C, and the pressure is 175 kilogram per square centimeter. And the reaction, you just put any information in here: hydrogen, nitrogen, ammonia, nitrogen 1, hydrogen 3, ammonia 2. And then in here, you can type the fractional conversion, which is a nitrogen in here, nitrogen, and the value is this one 0.41656. 0.41656. This one is a calculated nitrogen conversion, which is 0.8 times the equilibrium conversion. And then everything's finished, all input have been entered. Then don't forget to reset your simulation and then click next to simulate your process. Results available, no error found, yeah, only warning in here, which is okay. And then if you want to study more on the product, then you can go to the result summary of the stream, and then you will find out the R2 in and R2 out, and then you can check the conversion of the nitrogen in here. The nitrogen outlet should be 0.41 from the nitrogen inlet. Okay, that one is for the non-kinetic reactor. On the next video, we are going to learn the kinetic reactor. Thank you.